Hello and welcome to this video that goes through questions 6 to 10 of exercise 7e of the Algebraic Methods chapter in the Year 1 AS Mathematics Edexcel textbook. So question 6, a student tries to prove that x cubed plus y cubed is less than x plus y cubed, and the student writes x plus y cubed equals x cubed plus 3x squared plus 3xy squared plus y cubed, which is less than x cubed plus y cubed, since 3x squared y plus 3xy squared is greater than 0, and so identify the error made in this proof. Okay, so within this proof here, so the first part is correct, that is an expansion, but then the second part, it doesn't make any sense, because there's no proof that 3x squared y plus 3xy squared is actually greater than 0. Part B is going to use a counterexample to prove that. But essentially there is no evidence shown that this is true. So it's making a statement but without proving that statement. All it's done is expanded out x plus y cubed, and then you have to show some form of proof that this sort of inequality, so this statement, is actually true or not. So that's where the error is in the proof. If you can't support the claims, there's no line that supports that claim, or there's nothing in the question that supports that claim, then you cannot take that as true. So for example, they could have said in the question that both x and y are positive numbers. In that case, then you can use that implication to say that, okay, well then that part would be true. The 3x squared y plus 3xy squared is greater than 0. A counterexample that we have, a very straightforward one, remember that it's greater than 0. So if x is equal to 0 and y is equal to 0, then you get 3 times 0 squared 0 plus 3 0 0 squared, which is equal to 0. And therefore that's a very easy way of using a counterexample to disprove that. I'm trying to think of any other methods that we have that could be used. I think a lot of the negative ones will end up, some of the negative ones will work and some of them won't, but yeah, I'm not sure, but anyway, no x equals 0, y equals 0, so that's a perfect counterexample to prove that this is not true. The next one, prove that for all real values of x, x plus 6 squared is greater than or equal to 2x plus 11. So the way that I would personally approach this question is to go, well, why don't we have a look and say, well, x plus 6 squared is greater than or equal to 2x plus 11, and then let's expand out x plus 6 squared, so it becomes x squared plus 12x plus 36 greater than 2x plus 11, and then move everything over to the left hand side, so we get x squared plus 10x plus 25 is greater than or equal to 0. From here, I'm going to say that this is going to be b squared minus 4ac. So here, I'm going to check this out. So it's going to be 10 squared minus 4 times 1 times 5. And this is equal to 100 minus, times 25, sorry, minus 100, which is equal to 0. So therefore, b squared minus 4ac is equal to 0. So therefore, there is one real root. So that's how I can prove that the less than, the equal sign of this is true. And therefore I know that and I also know that if I was to sketch this new function, so when I've made them equal to each other, I know that essentially all values of this are going to be, so it's going to have a crossing point of x plus 5 squared. So I know that all that point is going to look like this. So all values are positive, 0 or positive. So what I've done is I've converted this sort of inequality into a separate quadratic, and then shown that that quadratic, I suppose, represents the points where the x-axis will be like 2x plus 11, and the y-axis is going to be x plus 6 squared, instead of being the usual y and x, because I put them together and then rearranged it, sort of changing what the x and the y values are. in essence what they're actually representing. So obviously you could draw x squared plus 10x plus 25 as a normal x and y graph, but here, because I've rearranged it, what it's sort of showing is this case, and we can see here that it's going to be the difference between them here shows that there's 0, that's where the meeting point would be between them. Then the rest of it shows that x plus 6 squared is always going to be greater than the 2x plus 11. But there is another way of showing it in the answer. This way is not a very clear way, to be fair. It's not a very intuitive way to use, but it's something to think about in the future. So if we use x plus 5 squared instead, is greater than or equal to 0. So in this case here we get x squared plus 10x plus 25. And then we have the next step then is to go, well, what's x plus 6 squared? So x plus 6 squared is equal to x squared plus 12x plus 36. And if we do x plus 6 squared minus x plus 5 squared, we get x squared plus 12x plus 36 minus x squared plus 10x plus 25. So from here we end up with x squared minus x squared is 0, 12x minus 10x is 2x, and 36 minus 25 is 11. So here we know that the difference between them is always 2x plus 11, so therefore x plus 6 squared has to be either equal to 2x plus 11 or greater than it. And that can show you for all real values of x as well. Not as an intuitive way, but it's sort of a technique that you can see. Question 8, given that a is a positive real number, prove that a plus 1 over a is greater than or equal to 2. So the first thing I probably want to do here is get rid of the a. So I'm going to multiply both sides, everything by a. So I'm going to get a squared plus 1. Now here's the interesting thing, is that if I'm multiplying across, I keep, and this is where the watch out thing is, I keep the inequality the same. So the inequality does not switch direction as a is greater than 0. Remember, if a was negative, then I would have to rewrite this as a squared plus 1 is less than or equal to 2a. Because the fact a is negative, remember when you times a negative number across, it switches the sign of the inequality. So that's the key facts that you're going to use here. From here, it's just a basic step of a squared minus 2a plus 1 is greater than or equal to 0. And then from here, we're going to factorize. So it's going to be a minus 1 squared is greater than or equal to 0. And that is enough to prove, essentially, that a minus 1, so all values of a are going to be bigger. The reason why it's bigger as well is because it's a squared number, so all squared numbers are greater than 0. So therefore we know that we've proven that this holds true. Again, these questions are not easy, they're not always intuitive to do. The more practice you do, the more you'll start to see these little patterns as you go through with them. But the key thing here is that, again, this inequality doesn't change, and then by proving that one side is a square number, so here we've just factorized it and we found that it's x minus 1 all squared, so therefore we know that for every value of a, it must be greater than or equal to 0, because a minus 1 squared always gives you that value. So yeah, we've manipulated the equation and we've got our proof. Question 9, prove for any positive number p and q, p plus q is greater than 4 pq. So for this one, I would start from getting rid of the square root, because that's not going to help us. So if we square both sides, we end up with p plus q squared is greater than 4pq. And then from here, we can expand out our terms. So it's going to be p squared, well, I don't need the bracket, sorry. So it's going to be p squared plus 2pq plus q squared is greater than 4pq. Okay, so from here we have got our, okay, so we need to think about how are we going to get this result. Let's go back, check on the proof for any positive numbers. So if there's any positive numbers, for all positive numbers, if p minus q all squared must be greater than 0. So we can rewrite the left hand side, we can expand this out. So it's p squared minus 2pq plus q squared is greater than 0. And therefore, if we were to compare this side and this side, we know that if we wanted to substitute in p minus q squared, we would then have to say, well, this is the same apart from the difference between p minus q squared and p plus q squared is the minus 2pq going to 2 plus 2pq, so it must be 4pq. So essentially p plus q squared is equal to p minus q squared plus 4pq. So if you add plus 4pq to the left to this equation here, which is p minus q squared expanded, we end up with plus 2pq, which matches our p plus q squared. So therefore we can say that p minus q squared plus 4pq greater than 4pq, and therefore we can say, if we subtract both sides, we can say that p minus q squared is greater than 0. So that's how I've done it to prove essentially this statement that p minus q squared is greater than 0. So by expanding it out, going through it, solving it, and then we end up with p minus q squared. If p minus q squared is greater than 0, then we can go to here and we can say, well, if p minus q squared is greater than 0, therefore this must be at least a positive number, and then we're going to add a positive number here. So therefore p plus q squared are going to be greater, but we therefore from here we can say that p plus q squared is going to be greater than or equal to, so p plus q squared is greater than or equal to 4pq. So to get that definition, we know that essentially we use this idea that so p minus q squared is always a positive number. So we can use this idea that p minus q squared is positive plus 4pq, which is positive. So therefore, if this is a positive number, it means that when we substitute, so essentially what we've written in this line is the same as what we've written at this line here. So of course, if we've got p minus q squared, which we now know is a positive, and plus 4pq, which is similar to the right hand side, therefore this must be held true. As long as p, which we're told in the question, p is greater than 0 and q is greater than 0. And we have proved our statement. It's a bit of a messy proof, this one, it's not perfect, but again, your proofs don't have to be perfectly written out, and they might be a bit messy when you write them out. For part B, show by means of a counterexample, this inequality does not hold when p and q are both negative. So if they are both negative, we just, let's say p equals minus 1 and q equals minus 1. So minus 1 is equal to minus 2, and root 4 times minus 1 is equal to root 4 times 1, which is equal to 2. Minus 2 is less than 2, so remember that's the same as p plus q, and this is the same as 4pq, so therefore you have disproven your statement by counterexample. Question 10, it is claimed that the following inequality is true for all negative numbers x and y. X plus y is greater than or equal to root x squared plus y squared. The following proof, so they've squared both sides to get x plus y squared is greater than x squared plus y squared, and then x squared plus y squared plus 2xy is greater than or equal to x squared plus y squared. So 2xy which is true because x and y are both negative, so xy is positive. So the issue that they have forgotten is that if they are both negative, that means that the left hand side of the equation can be, this one can be negative, but this one can be positive if they're both negative. In fact, let me see. So this, so x plus y, so x plus y here could be negative. So if we could have, so if we have x plus y, these two are negative. So that's negative and negative. So that's going to give you a negative. So neg plus negative is equal to a negative, because you'll have like -1, -2, which is -3. But here, this one is both positive numbers, because you've got x squared. So x squared can be made up of the positive version or the negative version of x. So they both potentially could be your positive answer. So therefore, in that case, the inequality is false. And this can actually be more easily proven by the fact that if you plug in, so let's say we have x minus 1 so x equals -1, y equals -2, then here this will be -1 squared plus -2 squared, and this gives you root 1 plus 4, which is equal to root 5. And this is not true then, because then x plus y is -3, and root x squared plus y squared is equal to root 5. So therefore, -3 is less than root 5. So therefore, this first line is not true at all. So we kind of answered two questions there, part A and part B. Prove that this inequality is true if x and y are both positive. So we know that x plus y all squared is equal to x squared plus 2xy plus y squared, as shown in the question. So we know that x is greater than 0, y is greater than 0, and therefore 2xy must be greater than 0. So we could say here, so from here, the x squared plus 2xy plus y squared is going to be greater than x squared plus y squared. And then we know that we've got, what do we have here? We know that this is the same as x plus y all squared is greater than or equal to x squared plus y squared. If we square root both sides, we end up with x plus y is greater than or equal to the square root of x squared plus y. So essentially we put back our x squared plus y. We prove basically that this expansion here, all the values are greater than 0, so that gives you a positive answer. So we've proven that the left hand side is completely positive. We've also proven essentially that x squared plus y squared must be positive because they're all greater than 0. So therefore we plug it back in, we plug back in our x plus y squared is greater than or equal to x squared plus y squared, and then we square root to get our answer, and that is enough for the proof. Okay, that's the end of this video. If you have any further questions, please let me know.